All right, good morning and welcome to Office Hours, Week 3. I am ready to answer any and all of your questions. Looks like I'm the only one in the chat right now. I haven't taken a look at my email yet, so I'm gonna give that a look and see if any questions are waiting there. But as always, if you're here live, I will give you priority over. Oh, we have one live one. Good morning. All right. Oh, okay. Sorry, I just saw your the question that you sent in over email. Let me show you why the final answer has 4 significant digits. So this is a question based off a homework problem. And it says 2 naturally occurring isotopes exist for the hypothetical element dipium. 25%, 25.0% of dipium atoms have a relative mass of, let's see, what was that? 17 AMU, 17.0 AMU, and 75%, 75.00% have a mass of 21.30 AMU. And we're asked to determine the atomic mass based on these relative masses and percent abundances. So let's go ahead and take a look. All right, so this is similar to the problem that I did last office hour, which was Saturday. So what we have to do here, just freeze that. All right. So I'm going to open up a new page. So we need to multiply each atomic mass, right? The mass of each isotope. So one is 17.0 AMU, and the other is 75 point. No, sorry, that's the percentage. The other is 21.30 AMU. And we have to multiply each by the percent abundance, but we have to do this as a decimal. So it's 25.0 over 100. That's how you convert a percentage to a decimal, is you multiply, or you divide, excuse me, by 100, and then we multiply the second one by 75.00. Divide that by 100. So let's go ahead and look at, let's crunch our numbers, and then we're going to add these two together after we multiply each isotopic mass by its percent. So 17.0 times 25.0 divided by 100, comes out to be 4.25 AMU. When you look at the rules for significant figures, there we go. 17 has 3 significant digits. 25.0 has 3 significant digits. So 4.25 should have 3 significant digits, and it does. So we don't need to add zeros. We don't need to round. Well, we save rounding to the end, but I'm putting 3 lines here to remind myself that that number does indeed have 3 significant digits. Let's do the second multiplication. 21.3 times 75 divided by 100. This is 15.975. All right, and again, let's look at our rules for significant digits. We have 1, 2, 3, 4 significant digits in our isotopic mass. We also have 4 significant digits in our percent abundance. So our answer can only have 4 significant digits. I'm going to wait to round again to the end, but I'm adding these lines to remind myself that this number has 4 significant digits. This number has 3. Now let's add these two together. 15.975 plus 4.25 comes out to be 22.225. Now, when you apply the rules for significant digits, one thing you'll notice is both of these numbers have their last significant digit in the second decimal place, which means that we have to round our answer to the second decimal place, and 5 rounds up. So the correct answer, this is the correct value, but the correct value with the correct number of significant digits is 22.23, and then the correct units are AMU. So this is the correct answer. And Saturday, probably what happened with you on this problem, and the reason why you thought it was 20. Wait, oh, I'm sorry. I messed up here. It's not 22. This is a 20. There we go. Probably the source of your confusion is you only look at the total number of sig figs in a number when you're doing multiplication and division, and that's what we did in the first 2 steps here and here. We had 3 significant digits, so our answer had to have 3. The second multiplication, we had 4 significant digits, so our answer had to have 4. But in the second step, these are the rules for addition and subtraction. And you don't look at the total number of significant digits, you look at the last significant digit in the number. 4.25 has its last significant digit in the second decimal place. 15.975 has its last significant digit in the second decimal place. So our answer must have its last significant digit in the second decimal place, and that's the place we round to. Yeah. So precision is determined by the last significant digit in the number. Precision is literally the reason why the correct answer is 20.23. Because it has to have its last significant digit in the second decimal place. So if you look at sodium arsenide, well, if you look at the periodic table, first you have to look at sodium. And sodium wants to be like its nearest noble gas, neon. You can see that sodium has 11 electrons, neon has 10. So sodium wants to lose one. After sodium loses an electron, it'll have a charge of +1. Then if you look at arsenic, As, it has 33 electrons. It wants to be like its nearest noble gas, krypton, which is 36. So arsenic as an ion, when it turns into arsenide, wants to gain 3 electrons. So as an anion, arsenide will have a charge of -3. And then what you have to do is you have to look at the charges and ask, how many positive charges do we need to balance with our negative charge? The answer is 3, because +1 goes into 3 times. So Na3As. All right, so so one thing that I can't do is just do the homework for you. So I see that you're going through homework 3, and I can't answer them question by question for you. So I can answer questions on you're not sure how to do something or specific type of calculation, or you're not sure about how to name ionic compounds or whatever. I'm totally down to help teach you, but I can't do your homework for you. No, no worries, dude. I'm more than happy to help clear up understanding things or explain stuff, or I will totally work homework problems out of the textbook that you have questions on. Um, but I can't solve homework problems before the assignment closes. Sure thing, absolutely. And I'm also, by the way, working on a. I'll be posting in Canvas in our announcements, kind of a breakdown of what to expect on the first exam. I'm just wrapping up its construction as we speak. So it's going to be very much like the prereq exam. All my exams are basically formatted the same. So there's going to be multiple choice questions. There's going to be numerical answers, numerical entry. Are the two question types. It's going to cover chapters 2 through 4, I believe. Let me double check that. Oh, sorry, not 2 through 4, 2 through 3. There we go. No, chapters 1 through 3. There we go. Oh, wait, hang on. Yeah, let me just double check the syllabus. There we go. Syllabus is the most reliable source of information. chapters 1 through 3. There we go. Chapters 1 through 3. Yeah, the questions are going to be multiple choice. I believe I'm putting on the finishing touches to it, so I'll be releasing a comprehensive Canvas post about this. But it's going to have approximately 32 problems. I don't know how long the exam is going to be at time-wise. I don't know how much time you'll have to solve it. Part of the reason why I don't know how long it's going to be yet is because I need to take the exam myself. The way I time the exams is I take the test, and by take the test, I mean I physically write out every problem. I punch in the numbers to the calculators, do every single thing, every single step, and then I time myself to see how long. And I'm not racing through it, but then the amount of time that it takes me to take the exam, I double that, and that is the amount of time that you have to take the test. And I'm not doing this, I'm not saying this to like flex on anybody or like, oh, I can do it in double the time. Of course I can. I wrote it. I know how to do these problems. The reason why I time myself and then double it for your time is what I'm doing when I take the test is I am physically measuring how much time it takes to write out every step, to punch in the numbers into the calculator. Because in an exam situation, when I'm taking it, I'm not having to think on how to do these problems. I instantly know. So I double it so that the total time that you have to take the test, half of that will just be physically doing the problems. It gives you the other half of the test time to think your way through the problem. So that's kind of my testing philosophy. If you ask, most of my former students will tell you that time is definitely a crunch on my exams. Time definitely is challenging, but that's how I determine how much time goes into the test. Which again, I haven't timed this one yet, so I don't know how long. Nope. So, when I teach in person, right, when you're taking physical exams written on paper, showing your work is clutch. But there's no way to do that with Canvas. I don't require you don't have to submit your scratch. Your grade is based on whether your questions are right or wrong. Which is good and bad. There's no points in showing your work, so you don't have to worry about doing it. If you can just know how to do a problem, do it fast, more power to you. But your points are earned on the correctness of your answer. And every correct answer has three things, right? There's units, the value, and the SIG FIGs. You have to have all three to have the correct answer. And it's an all or nothing kind of deal. Again, too, that's also Canvas based exams have a different style than my in-person exams. My in-person exams tend to be not as many problems, like maybe 8, and they're all word problems, and they all, have multiple steps, and you show a ton of work. In Canvas, it's multiple choice and numerical answer. So I can't really ask complicated questions. So it's just short little bullet questions, right or wrong, full credit or 0 credit. And that's the way things go in an online testing environment. Excuse me. Yeah, the chapter 1 material. So you're totally right. Lecture dives directly into chapter 2. The chapter 1 material that's on the exam. Let me pull it up real quick. The chapter 1 material that is on this exam touches on 2 topics. One is unit conversions, which we've done plenty of in lecture. And lab, and unit conversions are just all over this course. And the second chapter 1 topic that's on the exam, which technically it's chapter 1, but it's also technically in other chapters as well, is density. Which density has an equation. Density is equal to the mass divided by the volume. And so density then just becomes an algebra problem, which involves sig figs and unit conversions. So anyways, that is the chapter 1 material. In lecture, we dove straight into chapter 2. But we've done plenty of unit conversions, and density has been part of the course. So those are the chapter 1 concepts, which you've already dealt with in the class, that are on exam 1. And if you want more practice in these, something that you should know is if you're looking for additional practice heading into the exam, try the chapter 1 practice homework. From the text. So the exam covers chapters 1, 2, and 3 from the textbook. Um, so any of the homework, excuse me, problems on homework 3 that are involved in concepts from chapters 1, 2, or 3 will definitely be on the exam. So for example, you're asking me about naming ionic compounds. That's chapter 3 material for sure, or determining ionic charge. That's chapter 3 material. So that stuff will totally show up on the test. Oh, you know what? I think I messed up. Well, actually, sorry. I need to double check a couple things. Anyways, I'll be posting a more an exhaustive. Okay, so I need to confirm something really quick. Wait, hang on. Something's off in the syllabus. I'm just noticing that it says exam 2 is on chapters 5 and 6, but it says exam 1 is 1 through 3. So what I need to figure out is, did chapter 4 fall on exam 1 or exam 2? And I will clear this up in my post on exam 3, which should be coming out a little later today, at the latest tomorrow. Because I'm not exactly sure whether chapter 4 gets covered. We talk about it in lecture. Spent a couple lectures on it. The question is it exam 1 or exam 2? Probably exam 1, looking at the lecture schedule. But again, I'll confirm that later. Yeah, sure thing. A couple questions. Is there a specific Lewis structure you'd like me to do? Oh, okay, like the Lewis structure of an actual atom. Sure thing. All right. So the Lewis structure for an atom, you can determine it a couple ways. One, you can look. So if you look at the electron configuration, for example, for nitrogen. All right. If you look at the Lewis structure, so if you look at the electron configuration for nitrogen, nitrogen has a helium core if we're writing electron configurations with the noble gas abbreviation. It is down on the second period, so 1, 2. So this would be 2s2, 2p3, because you move starting here 1, 2 spaces through the S block, then you jump over to the P block and you go 1, 2, 3. That's where that 3 comes from. All right, so that is where the electron configuration comes from. And if you know the electron configuration, oops, hang on one second. I'm just fixing my layers here. There we go. All right, so so that's where the electron configuration comes from. Now, to draw the Lewis structure, in a Lewis structure, we are only concerned with our valence electrons. And the valence electrons are defined as the electrons in the highest energy shell. So the highest energy level, all those electrons are our valence electrons. So here we have a total of 5 valence electrons. All right. Now, those valence electrons are represented as dots around the elemental symbol in the Lewis dot structure. And so we have to place 5. You start by, it doesn't matter where you start, but the fundamental way you look at the elemental symbol is there are 4 sides to it. You start by placing dots. So 1 on each side, 2, 3, 4, and then once you've put 1 on each side, you start doubling up. 5. So the Lewis structure for nitrogen looks like this. All right, that is the Lewis structure for nitrogen. Now, if you're wondering, is there an easier way? Is there a simpler way? Do I have to write the electron configuration out every single time? The answer is no. I start using the electron configuration because that is a familiar kind of jumping off point. We've been doing electron configuration, so it'll seem familiar and it's easy to look at and go, oh, that's where the valence electrons are. That's where they come from. Here's the fast way to determining a Lewis structure. All right, you can do so. So Lewis theory is something that's exclusive to the main group. All right, it doesn't really explain the structure or reactivity of the transition metals, so that's where molecular orbital theory comes in, but it does do a good job of explaining the behavior of the main group elements. So as a reminder, the main group includes the first two rows of the periodic table, and then kind of the other side. It's the S block together with the P block. All right, and actually for the purpose of Lewis dot structures, helium really belongs in that second column. It's placed all the way to the right because it is a noble gas, but as far as its electron count goes, it has 2 valence electrons. Now, here's the fast and quick way to determine the number of valence electrons that'll be in your Lewis dot structure for an element. All you have to do is count what column on the main group it falls in, and that'll tell you the number of valence electrons. So, for example, this is column 1, column 2, column 3, column 4, column 5, column 6, column 7, and column 8. All right? If an element falls in whatever column of the main group an element falls in, that is the number of valence electrons it will have. That is the number of dots in its Lewis structure. So one thing that you notice immediately is nitrogen is in the 5th column. It has 1, 2, 3, 4, 5 Lewis dots. All right. We can grab any element out of the main group. So let's do let's do a weird one. Let's do astatine. You probably didn't even know that AT was named astatine. But all you have to do is look at the column it falls in. It's in the 7th column. That means that astatine will have, and again, you'll look at it as having 4 sides, and you start putting 1 electron at a time. 1, 2, 3, 4, 5, 6, 7. There's the Lewis dot structure for astatine. Let's pick another weirdo. Why don't we do, I don't know, germanium? One, 2, 3, 4, right? Because we're doing 1 on each side. Germanium is in the 4th column, so it will pick up 1, 2, 3, 4 valence electrons. By the middle columns, so if you mean the columns in between here, so like this whole region, and these guys down here, yeah. So for all of these guys, you will never do Lewis structures. With these. So Lewis, I will only ever ask you about Lewis structures for the main group elements. The reason why is Lewis theory provides a robust and a good explanation for the patterns of bonding and reactivity that we see for main group elements, so everything boxed in green. The transition metals in between the two blocks of the main group and the lanthanides and actinides, which are down here, their reactivity cannot be explained by Lewis theory alone, and so I won't ask you to do any Lewis dot structures with elements from those columns. So those are out of the picture. You don't have to worry about those. Dude, Saturday, thank you for asking tons of great questions this morning. I got to run because office hours are up, and I have a 2-year-old calling my name. But thank you for dropping by. Look for the post on exam 1. It'll be coming out again later today or tomorrow at the very latest. And I'll catch you all next week. Later.